Hello. So today I will be going over how to find absolute extreme points, so either minimums or absolute maximums. So to do this, we need a thing called a LaGrange multiplier. So the general formula how to find this, you have to take the gradient of the function that you are given, and then you have to take this lambda. This is called lambda. This is called your LaGrange multiplier. Take the gradient of your constraint function. So what do I mean by that? So this is an important concept to remember. So remember, if you have like a certain curve in the XYZ plane that is gonna shine down on it, or you could have like something passing the XY plane and it's gonna shine on it, and then the function that's surrounding it is called your like your region, or in this case your constraint. So to do this, we first gotta take the gradient. So let's take the gradient of f. So if we do this, we take 3y, then we take 3x as our gradient. Okay, and now our other gradient, we can call it g. So to x, it will be x over 32, and then y over 2 over 9. Okay, so now we need to set them equal to each other. So 3y, 3x is equal to the Lagrange multiplier, that's a scalar, times the gradient of this. So x, 36, 2y, to 9. So let's see. I think maybe the best way to think about why this works is saying that the gradient of the region, so it would be a certain vector, right, is equal to the scalar of the gradient of the function. So when both of them are equal, when both of these gradients are equal to each other, in terms as long as they're equal in terms of like a multiplier, so like a certain scalar, they're gonna that means that's the absolute lowest point. So that makes sense because if if the gradient and then if the gradient of the function and the gradient of the path equal each other, remember, and the gradient is the steepest path. So maybe so the way maybe to interpret it is, oh, that's the steepest path, so it's gonna have the greatest is gonna have the most like extreme like curvature to it. And at the same time, you have to remember that the gradient is shining down on it, creating a normal vector. Orthogonal to a normal vector to that. So if that's the best way I think I can try to visualize it, or make sense out of this formula. Okay, so now all we have to do is set them equal to each other. So let's set each component equal to each other. So now we got 3y is equal to the Lagrange times x, 32, and then the other component 3x equal to the Lagrange 2y, 9. And then there's an issue. We have three unknowns and we have two equations. Well, we do have another equation technically. We have this one. We have our constraint. We can use our constraint as our other function. So we can say, okay, x squared over 64 plus y squared over 9 equals 1. So now this problem literally came from calculus and now it's all system of equations. So there's a variety of ways we could do this. Maybe what I'm maybe thinking, maybe we could set this y isolated, right? Take this LaGrange x, and then 3 times 32, that's 96. And then we have an equation for y. So now let's try to substitute it into here. Actually, never mind. Scratch that. Let's set this function equal to the Lagrange. Because the reason why I want to do that is because I want to utilize this function. This function doesn't have the Lagrange. So maybe in a way I can get rid of the Lagrange. It can help us use this function. So let's set it equal to the Lagrange. So we can say, okay, so this Lagrange is equal to 3y over x 32. Remember it's very, oh sorry, this is 96. So 96. So I always feel a little iffy about doing this because I don't like to have variables in the denominator, just because if it's a zero, you can make that function defined. But I think it should be fine here. So now we can substitute this Lagrange into here. So now we have 3x is equal to 96y x times 2y over 9. Okay, so let's see. Maybe we can set this function equal to x, right? So let's take this x and put it here. So we have x squared, and then this is 90. Oh, so let's change it to 192. 192y. 192y, and then this 3 came down here. This became a 27. Okay, so now this is good because look, now we have, I'm saying that x squared is equal to this function, to this equation, and now I can substitute x squared. Look, we have an x squared right here, so we can substitute all of this into here and be everything that relates to y. So now we can solve what y is. Okay, so let's do this. So 192y, just making sure that I did everything correctly. So yep. Oh, look, so that should be a y squared. Sorry. It should be a nice I squared. So x came up here. Yep. And then actually we can even try to simplify 192 over 27. That will give us 64 over 9. So let's get rid of this. 64 over 9 y squared. Oh, look, this is awesome because we substituted this into here, And now remember, this is 1 over 64 plus y squared over 9 equals to 1, right? So this 64 will actually cancel out, and we're going to be left with this over this plus y squared equals 9 equals this. Okay, so now we can do 9 over y squared, well, this would be 2, equals 1. So now we will have now we have 9 over 2 square root, which is plus or minus. Another thing, we could test out the plus or minus, but just for simplification ways, let's assume that x is greater than 0 and that y is greater than 0. So let's don't worry about this negative. We can, we can always substitute it and see what we get, but we don't have to worry about it right now. Because we're just saying this is in the first octet. Okay, so now we have this y equals 9 over 2. And look, right here I have a function that's all in terms of x and y's, and I already have it set to x. So we can substitute it. So we can put 64 over 9. Substitutes is 9 over 2 squared. So this will go away, 9 over 2, x squared. So now this 9's will go away. This will become a 32 x. So those are our two values. Okay. So now what we have to do is plug these values into the original function. So what's our original function? Our original function is 3xy. So 3 is equal to 3xy, so the 32, times the y is this one. We can actually take that 9 and send 3 over square root of 2. And then if we simplify it, we can have 9 square root of 32 over square root of 2, which this can simplify to 9 over square root of 16. This 16 will become a 4, so 4 times 9 is 20. It's 36, and then we have it. So our maximum is 36 at these points. So that's how you use a LaGrange multiplier. We don't need to solve for the LaGrange. So all that is just a multiplier to help you solve this system of equations. That's all it is for. Okay, that's all. Thank you. And so next we're gonna go to multiple integrals, and we're gonna be going over rectangular coordinates, spherical coordinates, math problems, and regular like integrals that have like functions with them. Okay, thank you.